So now we talk about the factors which affect the resistance of a conductor. The factors which can affect it are the length of the conductor. Then at this end we can see the thickness, which can be represented by this circle out here, and this part we call as cross section. What we see from the front is called as the front section, but what we see from the side is called as the cross section. Just imagine this thing out here. From the front what you see is a front section, but when you see it from here, this part is called as the cross section. So cross section helps us to understand the thickness of the conductor. And obviously another important factor is the material with which the conductor is made. Let us go step by step. First we will talk about the length of the conductor. So if I talk about length, it's quite simple to understand that if I have two conductors of length, let's say L, and the other one is of length twice of L, the resistance experienced by an electron in this conductor will be more than the resistance in this conductor, which means that if the length of the conductor is increased, the resistance also increases. So we can say that resistance is directly proportional to length. Then we talk about the another factor, that is area of cross section. When it comes to that, let's say I have a conductor with area of cross section A, and there is another conductor with area of cross section twice of A. As you can notice, the length of both of them is almost same. But the one in which the area of cross section is more, the electrons will find it easier to avoid collisions. And if it is easier to avoid collisions, tell me, will the resistance be more or less? Well, you guessed it right, the resistance will be less. That means if the area of cross section is more, the resistance will be less, and if the area of cross section is less, the resistance will be more, which means they are inversely proportional to each other. So resistance is inversely proportional to area of cross section. Now the last factor out here is material. When it comes to material, same dimensions of different material will offer different resistances. For example, if I take a wire of 2 meter length and 1 meter square area of cross section made up of silver, then it will offer less resistance as compared to that of copper. That means different materials will offer different resistances. Now that we have understood the concept of resistance and the factors affecting the resistance, let us focus upon the last aspect, that is the material. To understand the concept of how material affects the resistance, we will have to deal with another very important topic called as resistivity. So let us consider a metallic conductor whose length we can assume to be 3 meter and whose area of cross section we will consider to be 1 meter square. Now these zigzag lines inside this particular conductor, they represent the resistance of any conductor. So that means from now onwards, if you want to express the resistance of any conductor in a circuit, then you can do that by drawing zigzag lines like these. Now just imagine if I cut this conductor in 3 equal parts. In that case we will get 3 different conductors. Let's say one of them is this. So now this conductor will have a length of 1 meter and its area of cross section will be 1 meter square. Also, this will have some part of the resistance of the total resistance present inside the entire conductor. This small resistance present inside unit length, that means 1 meter length, and unit area of cross section, that means 1 meter square area of cross section, is called as resistivity of the conductor. So to understand this in further detail, let us obtain the entire formula. We have understood earlier that resistance is directly proportional to length and inversely proportional to area of cross section. To remove this proportionality sign, we will introduce a constant, and the constant which we use is a Greek letter rho. So we have a formula R equals to rho L by A. Well, this rho out here is called as resistivity. So that means resistivity is denoted by the Greek letter rho. This is the letter rho. It is written RHO. This is just for our reference. Generally we use only the letter. Knowing the spelling of it will not really help in the exams. Now let us express this same formula in terms of resistivity, that is in terms of rho. So I can write it like this, rho equals to R into A divided by L. As you see, A will go in the numerator and L will come in the denominator. Now, if we consider this as per the diagrammatical representation here, and I take area as 1 meter square and length as 1, then it is quite obvious that rho will become equal to R. That means resistivity is equal to the resistance, but in a specific condition, that is when area is 1 meter square and length is 1 meter. That means what was present inside the entire conductor out here was the resistance, but here in unit length and unit area of cross section what is present is resistivity, that is rho. So that means we can now define resistivity as resistivity is defined as the resistance of a conductor of unit length and unit area of cross section. With that, we have understood that these two things are a bit different from each other. Resistance can be for any length whatsoever, but resistivity is only for unit length and unit area of cross section. Apart from that, if I talk about the unit of resistivity, then even the unit is different. As you know the formula we have written, rho equals to R into A divided by L. Here the unit of resistance is ohm. The unit of area is meter square and the unit of length is meter. So if I cancel out the meter out here, so we get the unit of resistivity as ohm meter, which again helps us to understand that the unit of resistance and resistivity is also different. Resistance is denoted by the unit ohm, whereas resistivity is expressed in ohm meter. So by all these things, we can conclude that resistance and resistivity are different from each other. Now that we have understood the concept of resistivity, it helps us in understanding that resistivity is a material specific constant. Whenever we change the length or area of cross section of a conductor, the resistance will change, as we have already understood, but what will not change is its resistivity. Each material has a different resistivity. For example, the resistivity of silver is 1.60 into 10 raised to minus 8 ohm meter. If I talk about copper, the resistivity is 1.62 into 10 raised to minus 8 ohm meter. As we go on in the list, the resistivity will start increasing gradually, and definitely if the resistivity increases, then the resistance of the resulting material will also increase. Here, since silver has the least resistivity, it will also offer the least resistance for a specific set of length and area of cross section. And that's the reason silver is considered as the best conductor. However, when we talk about the practical usage, as we know, silver is used mostly as an ornament.